Section 1.5 is to review the real number system. So there's quite a few things that's covered in the book on this section, but the main thing I need you to understand is what is the real number system. Okay, so let's start from understanding what types of numbers are called. So take for example the set 1, 2, 3, 4, and so on. This set is what you call natural numbers. Okay, so natural numbers begin from the numbers 1, there's no decimals involved, there's no fractions involved. Now, if you enlarge this set by just one number, okay, just by adding the 0 into the set, then this set has a new name. We now call it the whole numbers. So some students use the O and the 0 to help to remember, okay, as in whole has an O in there, which kind of looks like a 0. So that's your whole number system. Now, we can actually enlarge this system even bigger, so 0, 1, 2, 3, and so on. We can also involve the negative families. So again, you notice we are not talking about fractions and decimals, okay? So really we are talking about whole numbers, except that we allow the negative families in as well. And so we now have to give it a new name, yet a new name, okay? So this is called the integers. Okay, so as you can see, every time we enlarge the set, it gets a little bigger and we call it a new name. Now, there is a set which we call rational numbers. Okay, so what is classified in the rational numbers? Basically, rational numbers have to be numbers that look like A over B. Okay, they have to look like something over something. And the condition is that A and B have to be integers, so they have to be kind of like whole numbers. And they can be negatives, and the only thing is that the b, which is in the denominator, cannot be 0. So who are in the set? Okay, so what are the numbers in the set? So for example, the number 5 is part of a rational number, and the reason is because 5 can be written as 5 over 1. So 5 is in there. What about negative 3? Negative 3 is in there too, because you can call it negative 3 over 1. Okay. What about things like 1.5? 1.5 is also a rational number because you can write it as 3 over 2. So long as you can write it as something over something, it's a whole number. It's a rational number. Okay. What about the number 0? The number 0 is also rational because you can call it 0 over whatever, anything you like, 0 over 10. Okay. What else is in the set? Oh, things like 1.523. 1.523 is your terminating decimals, as in it's a decimal that stops. Okay, it doesn't go on, it stops. So because it stops, you can count the decimal places. There are 3 of them. So equivalently, that means your denominator has 3 zeros. And all these digits, you just put it on top. So it's 1523. So there you have it. You can write 1.523 as 1523 out of 1000. Okay, so when you write it like this, so again, it fits this role, okay, this model, which says that you have to look like something over something. So terminating decimals are also part of the group. So who else is in the group? Oh, things like this. You've seen this earlier. Root 49. Because what's root 49? If you think about it, it's like what times what gives you 49? 7 works, right? And 7 is 7 over 1. So he is rational too. Okay, who else is rational number? Now, this is an example we did previously, but let's pick something a little easier. So like 0.3333. So this is a recurring decimal, which we write as 0.3 bar. And for some of you, you may recognize this to be your 1/3. Okay, so again, it is possible to turn repeating decimals into fractions. So seems like this set of rationals has everybody in there, okay? It includes the positive, the negatives, even the 0, terminating decimals, repeating decimals. So who is not in the set then? Okay, so everybody seems like rational. So is there something that's not in the set? So the numbers that are not in the set is what we call irrational numbers. So basically these are numbers that are not rational. Okay, what are some of the examples? Some of the examples is like root 30. So if you recall what I told you earlier, root 30 is a radical term, but it doesn't transform into a whole number. Okay, if you take a calculator and press root 30, you will notice that it's a decimal that keeps going on, and there is no pattern. Okay, so these are some examples of irrational number. Another one that we use in geometry a lot is your pi. Okay, and pi, if you look at your calculator, maybe you should try. So if you press on your calculator, you notice that pi is approximately 3.141592654 and blah blah blah. Okay, and it doesn't seem to stop, and it doesn't have a pattern, so we can't use a bar. So it's non-terminating. So it has to be non-terminating decimal, as in it doesn't stop, and it has to be non-repeating, as in it doesn't have a pattern. Okay, so maybe in your high school days you have seen pi being represented by, let's say, 3.14, but watch out, it's not equal to 3.14, it's only approximate. Okay, sometimes we use things like pi is approximately 22/7. So these are all just approximations, they're not equal. Okay, so what is the value of pi? It's the decimal that keeps going on. So for that, we call it a new name. We call you the irrational numbers. Okay, so irrational numbers are basically the numbers that is not wanted. They are not wanted by rationals. Okay, and so you are not able to terminate and you're not able to repeat. So it's non-terminating and non-repeating. So when you put rational numbers and you combine with irrational numbers, then you have the real. So the real number system is really made up of, so let's see. So let's try to summarize this. Okay, so you're going to start the whole system as the real numbers, and under real numbers it breaks into two groups. The big group is the rationals, and the other arm is the irrationals. Okay, and who is under rationals? Integers is under rationals. So rationals include fractions and decimals. Integers does not. Okay, integers is only the positive, negative, as well as 0. Okay, and the next smaller set would be your whole numbers. Okay, because integers wants positive numbers, negative numbers, as well as 0. But whole numbers only wants from 0 and up. And the next smaller set will be your natural numbers. Now, this is what I need you to understand. So this pretty much tells you the hierarchy of the real number system. But I need you to think of it a little deeper. So take, for example, the number 5. Okay, so you notice that 5 is a natural number. It's also a whole number. It's also an integer. It's also a rational. And it's also real. So 5 sits over here. Okay, so 5 sits in natural, so he falls in all these categories. He's natural, he's whole, he's integers, he's rationals, and he's real. Okay, so you have to think in that sense. So any given number can possibly be in more than one set. So he can belong to more than one category. So I'm going to do an example with you to show you what you need to know. Okay, and how do you classify this? So try to take a few seconds here to memorize this connection. So remember, real numbers is the biggest set, and then you have the rationals and irrationals, right? And then it comes down to integers, whole numbers, and natural numbers. Okay, so let me show you an example. So let's have our classification. What do we have? We have okay, let's see. We started with natural, right? Natural numbers. And then I introduced to you the whole numbers. And after that, we enlarged the set a little more. We call it integers, which includes the negatives. And then we had a more collective name for them, which is called rational numbers. and then you're introduced to irrational numbers. Rational numbers. And then finally you're told what are real numbers. So let's draw a little chart and let's see if you understand why these numbers belong to these locations. Okay, so that's my chart. Okay, let's start with the first number. Let's talk about the number 0. Okay, is 0 a natural number? Okay, and the answer is no. 0 is not natural. Is he a whole number? Yes. Is he an integer? Yes. Is he a rational? Yes. Is he irrational? Nope. Is he real? Yes. Okay. So, what about the number 0.5? Now, 0.5, is he natural? Nope. Is he whole? Nope. Is he integer? Nope. Remember, the first three groups are really talking about numbers that are non-fractions, non-decimals. So is 0.5 rational? Yes. Okay, because it terminates, and as in it stops. Okay, so you can always write 0.5 as 5 over 10. So you can write it as 5 over 10. So yes, it does belong to rational numbers. So if it's rational, he cannot be irrational. Okay, it's one or the other, and it's real. Okay. What's another example? Let's try, let's say, root 3. Root 3, you notice, is not a perfect square. Okay, so as in what times what gives you 3. And it's got to be the same number too. So if you take a calculator and press it, it's going to give you something like 1.7 something something something, and it keeps going on. So is it natural? Nope, 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 because it's a decimal. Is it rational? Well, for you to be rational, you have to be either terminating or you have to be repeating. Okay, so you notice it doesn't repeat, it doesn't terminate, so no, you're not rational. But if you're not rational, means you're irrational. Okay, rational and irrational, they are just complements of each other. So are they real? Yep, they're real. Okay, so at this point you may be wondering, so it seems like everybody's a real number. Is there anything that's not real? Okay, so let me show you an example. For example, square root of -4. Okay, so equivalently I'm asking you, is there any number that when you square it gives you -4? Anything? So you think about it, if you have a positive number and positive number, of course you get a positive. Two negatives when you square it will also be positive. So there's no way you can end up with a -4. Okay? So is he natural? No. Is he whole? No. Is he integer? No. Is he rational? No. Irrational? No. And he's not real either. Okay? So -4 actually is another name. -4 square root. You may or may not have seen this, but this is really what we call 2i. So you're not going to be talking about this. So these are what you call complex numbers. Okay, so we will be talking about complex numbers, but not in this class. So maybe in your next math class, that's when you will see complex numbers. Okay, but right now, nope, we won't be dealing with that. Okay, so this is all I want you to know in 1.5. You need to know these 5, what is it 5? 1, 2, 3, 4, 5, 6 groups of numbers, okay, what they are. And what I could ask you is this particular number which it belongs to. Okay, so this is one way to ask you the question where I draw you the chart. That's an example, right? Let me show you the example. Another way I could ask you is in the set, say, 0, comma, -5, comma, square root of 6, comma, 3.8, comma, 2/5. Okay, that's my set. That's supposed to be braces. Okay, and then I say, okay, can you identify numbers that can be classified as, okay, natural numbers. So that's when you look into the list, okay, who is natural? Okay, 0 is not, -5 is not, okay, who is natural? None. Right? I don't have anything that's natural. Okay. What about whole numbers? Okay, so let's try a few parts. Whole numbers. Whole numbers. Who is under whole numbers? 0 is whole numbers, right? So what if I say, okay, which of these are integers? Okay, integers, we have a few more. We can be 0, we can be -1, like that. Okay, who are rational numbers? Okay, rational numbers. Okay, 0, -5. √6, if you press the calculator, is a decimal that doesn't stop. So remember, irrational is non-repeating and non-terminating. Okay, so it doesn't stop and it doesn't repeat. So √6 is not one of them. 3.8, it stops, so it is considered rational. And 2/5, it is rational because you can write it as a fraction. Okay, and that's it. So that's another way to ask you. So one way is to do the chart, another way is to ask you to list.